Hello everyone, welcome back to the NPTEL course on materials informatics. In this lecture we will continue our discussions on molecular dynamics. So just as a recap of what we did in the last lecture, we looked at molecular dynamics as a tool to examine the dynamic behavior of any given system, and throughout our discussions on molecular dynamics we are going to focus on diffusivity as a useful property for us to predict with molecular dynamics. Note that the objective of molecular dynamics is to track the trajectory of a collection of atoms in a given box in the presence of a force field. So the force field contains some external terms like let us say an electrostatic potential or something like that that your system is experiencing, along with interparticle interactions. So how individual particles or individual atoms are actually interacting amongst one another. So our objective is basically to track the evolution of atoms in this force field by solving Newton's laws numerically. But we did see that solving Newton's laws numerically is not a trivial task, and molecular dynamics can fail spectacularly even in a simple system. So we need more robust integrators, and velocity Verlet is a very useful integrator to start with. So we look at further aspects of molecular dynamics in this lecture. So the first aspect that we will sort of touch upon is how do we actually calculate the forces. So in the last lecture we looked at the fact that we typically use force fields, right, to calculate forces acting on individual particles, right, and we did see that there is an accuracy cost trade off with respect to using force fields. So in general the more complex a force field is, the more accurate it can get, but also the more expensive your calculation becomes. And in molecular dynamics generally the most expensive part of your calculation is the calculation of forces on the individual atoms, which is dependent on your force field, right. So just to sort of recap the workflow, right. So let us say you have a potential energy function which is given by your force field here, and given some kind of initial positions and velocities of your atoms at the given state of your system, you calculate the force acting on each atom or each particle, right. So the red arrow basically indicates the most expensive computational part, right. So once you calculate the forces, you then calculate the acceleration, you use integrators basically to calculate velocities and positions, and then you move all the atoms right to their new positions, and you assign the velocities of their new positions, and you keep doing this in a loop, right. So every time this loop is executed, right, you need to calculate force, and the force comes from this potential energy function or your force field, right, and this is the most expensive part in your molecular dynamics simulation. In terms of force fields there are actually various types. So as you go down up to quantum mechanical, you are actually increasing in the complexity, right, and also increasing in the accuracy. So pair potentials are some of the simplest force fields that you can come across. Lennard-Jones is a very famous force field. There are also Buckingham potentials. We look at how the Lennard-Jones potential looks like in the following slides. There are also multi-body potentials. So in pair potentials you consider only two body interactions. So an atom interacting with one of its neighbors one at a time, right. In multi-body interactions, multi-body potentials, an atom can interact with multiple neighbors simultaneously, right. So that is why they are called multi-body potentials, and so some of the examples are charm, EM and so on. There are also reactive potentials which are very good at modeling chemical reactions, so forming, breaking of bonds and so on. Very famous force field in this direction is ReaxFF. And then you can use quantum mechanical tools, so which is DFT or even beyond DFT calculations. So these four are fairly it's straightforward to understand that as you go down in this axis you have a higher accuracy as well as higher cost. Tight binding models are typically parameterized models, again usually on quantum mechanical calculations and so on. So you can think of this as sort of simpler physics based models, right. So they are not as accurate as quantum mechanical calculations, but they are faster, right, but they can certainly be more accurate than these some of these potentials, right. So tight binding models can also be used for calculating forces, and you can also use machine learning, right. So you can infuse machine learning, construct these intraatomic potentials or force fields, right, based on some kind of DFT data, right. And we'll take a detailed look at machine learned intraatomic potentials in the third module of this course in the advanced topics, but the basic idea is that machine learning can act as a bridge between your quantum mechanical tools and your sort of simpler force fields. because since you use machine learning, there is flexible mathematical functional form, so you can get accuracies that are very similar to DFT accuracies at the same cost as these kinds of potentials, same computational cost as these kind of potentials. So this can act as some kind of a bridge in your accuracy cost trade off, right. So you can include machine learning and also generate interatomic potentials. And the way these potentials, right, the pair, multi-body and reactive potentials are typically what are referred to as classical force fields or classical potentials. These potentials are typically fit to some kind of properties, known properties in your system, right. So those properties could be experimentally measured or can be computationally predicted using DFT or beyond DFT calculations. Okay, so what are some of the typical terms in a classical force field? So you can have a whole bunch of terms that sort of look like this. So for example, if you want to model a bond, something like a harmonic oscillator or a simple spring that is linked to two bonds, simple vibrational model, you can say this is k times, this is similar to x square here. Right. So k is your sort of spring constant in some sense. So you can model bonds like this. For angles you can also model, so for 3 body interactions you can model the angles, right. So these are the angular terms. For even higher body interactions, so 4 body interactions, you can model the dihedral angles. For improperly coordinated you can model some kind of solid angles here, right. And then if there are very long range weak interactions, you can have van der Waals interactions, right. And if you have strong electrostatic interactions, right, between atoms, you can also include that in your force field. So a force field can have a summation of several of these terms, right. So and each of them can have their own contributions to the ultimate potential energy, which then gives you your force acting on the atom and so on. So and you can also generalize this to other kind of interactions. So let us say you have magnetic interactions, sort of spin interactions, you can add an additional term and so on. So you can have several possible interactions all captured within your force field term here, right. And typically if you look at all of these kr, k theta, k5 terms and so on, the epsilon terms here, these are all terms that are learnable or fittable parameters, right. And these parameters are fit to some kind of known properties, so either experimentally measured or calculated properties. So if you know experimentally what the bond length is or what the bond strength is, the strength of this bond, you can basically determine what the kr term is, for example, right. So these are properties that are fitted or learnt, right. And then these are basically your features. So your r minus r equilibrium is basically the distance, right, of these bonds. The same thing, you have angles and so on. So you, in terms of machine learning framework, you can consider these terms, right, r minus rq theta, cos of n phi, omega and so on. These are your features and these are your weights or learnable values, right. And the product of these two gives your potential energy, right. So that is why classical force fields can be generalized very easily with machine learning tools as well. Okay, let us take a very specific example of a classical force field and let us see what kind of parameters or properties are actually used in fitting this potential. So we will take the case of Lennard-Jones potential. This has a very simple functional form. So your potential energy is basically given by this form 4 times epsilon, and then you have a sigma by r power 12 term, and then you have a sigma by r power 6 term here, right. So you can actually visualize, so your u, this is a pair potential. So your atom at your origin is basically interacting with other atoms that are sitting at a distance r away from it, right. And u basically gives you the potential energy associated with that pair interaction, right. So you can actually visualize your potential energy as a function of r, and you will probably get a plot that sort of looks like this. So the phi is the same as your u here. So at very short values, so very short r values, very short distances, this sigma by r power 12 term sort of dominates, so you get a very sharp spike here. At very large distances, your sigma by r power 6 term sort of dominates, right. And as r goes very large, you see that it starts going towards infinity. Your denominator becomes too high, and you will start asymptotically approaching this to 0. And at some intermediate values, right, you may see a minimum being formed at your potential energy, right. So you see that this kind of a functional form, this Lennard-Jones functional form, has two important parameters, right. what is the depth of your potential energy well. So what is the lowest energy that you actually get, and what is the position, what is the distance at which you are getting your lowest possible energy, right. These are the two important parameters, and those are your fittable or learnable parameters, your epsilon and sigma. So epsilon basically stands for your well depth, so the depth of your potential energy well here, and this is equivalent to the energy stored per bond, right, energy stored in the bond that you are modeling. And how can you determine the value of epsilon? So if you know the energy of that bond, you already know the value of epsilon. You can also get it from cohesive energy. So if you have a collection of atoms and you know the energy that is required to isolate all of those atoms, then you can take the average of the cohesive energy for per bond to get this epsilon term here. You can also use elastic modulus. So elastic modulus in some sense are related to the curvature of your potential energy as a function of atomic displacements, right. So you can if you know the elastic modulus such as Young's modulus or bulk modulus, you can actually determine the value of your epsilon here, right. And sigma basically is the interatomic distance or interparticle distance at which your energy is at the minimum, right, and if your energy is at the minimum, then your system is at equilibrium, right. So this is basically corresponding to the equilibrium distance between atoms, right. So if you know the equilibrium lattice constant, right, of your given structure, then you already know the equilibrium distance between atoms, so you can basically determine your sigma in a straightforward fashion. Both your epsilon and sigma, since they are derived from these properties, right, these properties can either be experimentally measured, so they can be experimentally known, or they can also be computed using density function theory or similar quantum mechanical tools. So DFT is quite good at let us say getting elastic modulus, getting cohesive energy and so on. It is also very good at getting lattice constants. So if you have a system where experimentally these quantities have not been measured, you can always compute them with DFT and use that to parameterize your sigma and epsilon terms, right. So this is the case for simple Lennard-Jones potential. As you keep increasing the complexity of your interatomic potential, you will have more and more learnable terms, so you will need more and more known properties of your system that you would need to fit those parameters. One final thing with respect to Lennard-Jones, so the sigma by r power 12 term basically indicates your repulsive term, and this sigma by r power 6 term basically indicates your attractive term, right, and that is why there is a negative sign here. So if the atoms are too close to one another, this term sort of dominates, your potential energy sort of blows up towards positive infinity, right, and if the atoms are closer to the equilibrium position or are far away, then the sigma by r power 6 term sort of dominates, because both terms become less than 1 at large values of r, right, and power 6 is usually higher in magnitude compared to power 12, and there is a negative sign associated with it. So that is why your curve is still in the negative region at larger distances. So this sort of indicates that if atoms are very far apart, they tend to attract one another, they try to form bonds. So if atoms are too far apart, they try to form bonds. If atoms are too close to one another, then they try to repel and push each other away, and at equilibrium distance there will not be any forces acting on the atoms, and the energy will be the minimum quantity. So there is perfect balance between your attraction and repulsion. Okay, so that was on interatomic potentials. The second aspect that we can think about when it comes to molecular dynamics simulations is the choice of time step itself, right. So we did see in the previous lecture that time steps can play a crucial role, and in general trajectory of any given particle tends to deviate from its actual trajectory at very large time steps. Right. So we should choose time steps that are as small as possible, so that we can still computationally sample relevant time scales, right. So if you have atomic diffusion, right, so diffusion usually happens in the of the order of nanoseconds to a few picoseconds. So you should try to at least your time scale of your simulation should at least capture those ranges, right. Similarly, if you have let us say phase transitions and so on, you may need to even sample larger time scales, right, in which case you need to do even more steps, right, in order to sample such time scales. So the general sort of rule of thumb is if the time step is too small, you may not have enough computational resources to explore all of the statistics that you want to explore, right. So if you use femtosecond time steps, right, and if your phenomena is of the order of microseconds, then you need to sample a billion steps, which may be computationally too large for you. And if the time step is too large, then the calculation can be unstable and you can have large deviations from the trajectory of your particles from where they should be, right. This we also see, we also saw in the simple harmonic oscillator example, where when we used larger time steps, we saw that very quickly the sort of the particles deviated away from their ideal trajectory. Right, especially with the explicit way of solving or the explicit way of integrating our velocities and positions. So if you use very large time steps, your trajectories can deviate away from their real trajectories very quickly, and the calculation can actually be unstable, right. So the choice of time step is fairly important in our molecular dynamics. So the general rule of thumb is you at least use a time step that is at least one order of magnitude smaller than the time scale of phenomena that is being captured. So this is general rule of thumb, but you try to always choose as small a time step as computationally feasible, right. So typical time steps that we use in molecular dynamics are in the range of about 0.1 to 10 femtoseconds. Right. So when you think of time steps, always think in the scale of femtoseconds, and then you are trying to sample phenomena that are happening around nanoseconds, at least. So you have to sample about 1 million steps, right. So if you are only interested in looking at translation of atoms such as diffusion and so on, then maybe 10 femtoseconds is good enough, because atoms vibrate on the order of picoseconds, and diffusion is basically where atoms vibrate and then one of the vibrations is long enough that the atom actually moves from one of its sites, its current site to an adjacent site. So it actually breaks a bond and forms a new bond. So in order to capture diffusions very efficiently, we need to ensure that our time steps are actually lower than the vibrational time scales of atoms. So it has to be lower than picoseconds for sure, and it is usually a good exercise to have about 10 femtoseconds or so as your time step. So if you are only interested in translation of atoms, 10 femtoseconds is usually fine. If you are considering molecules and if you are looking at both translation and rotation of molecules, then you need to reduce this a little more, maybe about 5 femtoseconds. If you are looking at torsion also in the case of flexible molecules, then maybe you need to reduce this even more. And if you are looking at pure vibrations, you want to model, let's say, some kind of phonon spectrum or vibrational modes, vibrational frequencies and so on, then you probably need even more accuracy. So you probably need to go to about 1 femtosecond or even lower, right. So these are the sort of rough rules of thumb. It's almost always a good exercise to explore a few different time steps and see for a small number of short simulations to see what type of different trajectories you get, and try to understand which time step is optimal. So you may have to choose a relevant time step for your system at hand based on some test calculations as well. But these are rules, rough rules of thumb that are useful to keep in mind. Okay. And in terms of molecular dynamics, apart from time step, there are also other typical sources of error. Some of them are addressable, and it's usually a good idea to spot these errors and address them so that you don't waste a lot of computational resources in doing wrong molecular dynamics simulations. One is that for whatever phenomena that you are trying to capture, maybe the simulation is not long enough. So if you want to capture diffusion, it's almost always preferable to go up to nanoseconds, right, of your time scale. And if you are only simulating a few picoseconds, then maybe you are not doing enough justice in trying to capture all the statistics associated with your diffusion process. So simulation not being long enough is usually one source of error, and this can also show up as deviations from your theoretical predictions compared to whatever you observe experimentally, right. Second is simulation cell not being large enough. So if you do molecular dynamics in very small cells, you may have high degree of correlations in how atoms are actually behaving with one another, and that may not be reflective of what happens in a real system, right. So if you have simulation cells that are very small, that may not reflect the actual dynamics that is happening in a real system, and you may have deviations in your predictions compared to what you experimentally observe. And both of these are sort of connected to your computational resources as well. So if your simulation cell is time is not long enough, then you need to spend more computational resources to increase the time. Same thing with the cell size also. So you may need to spend more computational resources to increase your cell size. Wrong time step is another source of error. So if you use too large a time step, you can have deviations that are very different, very large away from your actual trajectories, and you may get very wrong predictions as well. So wrong time steps is also something that you would like to avoid. And also wrong initialization of initial conditions of your system. So typically for liquids, right, we would like to have a random arrangement of atoms, and for solid the specific structure that you want to simulate for a solid actually matters, right, when you do a molecular dynamics simulation. So let us say you are interested in modeling ferritic steels, right, which are body centered cubic in nature, but if you give an initial structure of an austenitic steel which is face centered cubic in nature, then whatever trajectory that you are going to get, whatever dynamic properties that you are going to get with your molecular dynamics, starting with your FCC structure, face centered cubic structure, are going to be very different, very wrong compared to what you would have gotten if you started off with a body centered cubic structure. So when you are trying to simulate dynamics in solids, the starting structure really matters, right, in what kind of trajectories and what kind of statistics you actually get. So always pay attention whenever you are trying to do molecular dynamics in a specific system. Always pay attention on what is the initial condition, right, with which you are going to initialize your system in molecular dynamics, because small changes in your initial conditions can also lead to large changes in your trajectories themselves. Okay. So far we have looked at several possible things in molecular dynamics, but we never looked at temperature as a factor, right, and if you actually think about diffusivity as a phenomenon, right, diffusivity is highly dependent on temperature, right. So typically at lower temperatures you have very poor diffusivity of atoms, and as you keep increasing temperature, diffusivity generally becomes better in most solid systems, right. So diffusivity is a temperature dependent quantity, so which implies we need to introduce temperature within our molecular dynamics simulations. Second thing is, if you are interested in simulating phase transitions, right, phase transitions also occur at fairly well defined temperatures. So if you want to melt a solid and if your simulation is occurring at 0 Kelvin, I mean maybe you are not going to melt the solid at all, right. So unless you find a way to set your system temperature to be higher than the melting temperature of your solid, the solid is likely not going to melt during your simulation. So we need to once again introduce temperature in some way within our molecular dynamics. So recollect the fact that in simple density function theory, right, we always have our calculated results at 0 Kelvin. Right, and that is because we are always interested in solving for the ground state of the system, and the ground state of the system variationally occurs at 0 Kelvin, right. So when you have the lowest energy of the system, that is almost always guaranteed to occur only at 0 Kelvin, right. So in DFT the temperature is set very well, and that is at 0 Kelvin, right. But what about in molecular dynamics? So because we have to set a temperature somehow, so that we understand temperature dependence of various important quantities or properties within our system. So apart from diffusivities and phase transitions, chemical reactions can also get activated with temperature. So at low temperatures maybe a chemical reaction does not happen, and as you heat up your system to higher temperatures, they can get activated. So if you are interested in simulating any of these, you need to put into place temperature within your simulations. So we need to find a way to define temperature in the simulation and also find a way to control it, right, because we are solving Newton's laws, right. So we need to find a way to define temperature. And the way we actually determine temperature is actually using particle velocities, right. So here is where the equipartition theorem comes into picture. So equipartition theorem is quite popular among statistical mechanics and quantum mechanics, right. So this is where you sort of state that all the different vibrational modes that an atom can actually exhibit in a given solid or in a liquid contribute to the overall temperature of your system, right. So there is also some local equilibrium that is being assumed when you use equipartition theorem, but this sort of holds true for several systems, right. So with equipartition theorem we can basically state that your temperature, so you can write this as 3 n k, so 3 by 2 n kBT is basically your half mv square, right. So the kinetic energy of all the particles in your system, the cumulative kinetic energy, right, is basically related to your temperature of your system at a given time step t, right. N is basically the number of particles and kb is your Boltzmann constant. So this is basically your statement of your equipartition theorem. So we see that velocities of your particles are basically related to your temperature in a direct fashion. So depending on how you how the velocities actually evolve, you can actually track the temperature of your system, right. And you can also set the temperature of your system by setting the velocities, right. So let's sort of expand this understanding a little more. So let's say you want to set an initial temperature for your system. You can set the temperature by assigning maybe the same magnitude of these velocities, so the same speed for all the particles, but ensuring that the net momentum of the system is 0, right, because when you initially consider the system, you want the system to be at rest and not under net motion, right. The system can move over time, but when you initially start off with the system, you typically want the system to be at rest. And instead of assigning the same speed or same velocity for same speed, right, for each of your particles, you can also provide a distribution of speeds, right, such as using Maxwell-Boltzmann distribution and so on. So you basically define which speeds or velocities correspond to your temperature, and then you assign those speeds to all of your particles in your system, which should correspond to your initial temperature, right. Now if you do not add any constraints on your velocities, or if you do not add any constraints on your temperature will change over the course of your molecular dynamics simulation, and it will most likely approach some kind of an asymptotic value. So it will approach some value over a very large time scale. And this is how standard molecular dynamics is usually done. It is usually done in what are referred to as NVE conditions or an NVE ensemble, where the number of particles, volume and your total energy is kept constant, right. So number of particles is kept constant because you put all the particles in a box, the size of the box is kept constant, the volume is constant, and the energy is also kept constant, right. So the energy is basically the initial kinetic energy that you give. If there is no other external energy that is being input, right, then the energy will remain constant. There is no way for the system to actually exchange energy, right. So it's an isolated system. So it's usually done in some kind of an NVE condition, so which implies as velocities evolve with time, your temperature will also arrive at some asymptotic value. Now if you need to constrain the temperature, or if you need to control this temperature in your dynamics, then you need to use what is referred to as a thermostat, right. So using a thermostat, you can actually fix your temperature and control it during your simulation. So when you fix your temperature, you change this ensemble from NVE to NVT. So you fix the number of particles, volume, and also the temperature instead of the energy, because when you fix the temperature, you see that automatically the velocities get fixed, right, and hence your energy is no longer conserved. Because if your velocities are fixed or velocities are changed according to how temperature is changing, right, then the distribution of energy between your kinetic and potential energies will not be the same. So initially, let's say all the potential energy term is 0 and you only have kinetic energies, right, but let's say you are setting the temperature to be the same as your initial temperature. So you are controlling the temperature, which implies the velocities will always change such that the temperature is kept constant. So the kinetic energy term will always be higher irrespective of what happens to the potential energy term. So the kinetic energy term will be very similar to your initial kinetic energy irrespective of what changes happen to your potential energy term. Whereas if you did not constrain your temperature, whatever changes your kinetic energy term went through, those changes will be passed on to your potential energy. So if your kinetic energy decreased, your potential energy will increase. If your kinetic energy increased, your potential energy will decrease. But if you set your temperature, your kinetic energy is more or less set to be a constant value, and as the system evolves, as the positions change, your potential energy can actually shift, which implies your total energy of your system can actually change, and hence your energy is no longer conserved, right. So if you fix your temperature using a thermostat, you change your you change your boundary conditions of your ensemble of your system. We'll discuss more about ensembles in the next couple of lectures on statistical mechanics, and that's where we'll see how the changes with going from NBE to NBT actually make a big difference in what kind of properties you can actually compute in a given system. But keep in mind that temperature by itself is not fixed in molecular dynamics, in standard molecular dynamics. So if you need to fix the temperature, you need a thermostat. So how do thermostats typically work? So they work in fixing the temperature by basically scaling your velocities. So how do you scale velocity? So let's say you calculate your acceleration and you are actually calculating how to update your velocity, right? So you have calculated an acceleration, and with that acceleration you need to change your velocity, right? But before changing the velocity, you scale the velocity so that the system remains at the same temperature. So you do this process for each particle in your system. So you can define, so you see that temperature is roughly proportional to square of the velocity. So you can define some kind of a scaling factor for your velocity as the square root of the desired temperature to your instantaneous temperature, right, that you have in your system. So you always try to reach your desired temperature or keep your desired temperature as much as possible. And such scaling of velocities will affect the natural dynamics of your system. So naturally the system wants to update its velocity in some way, but you are changing the velocity so that your system's temperature is being maintained. So in other words, you are changing the energy available in your system. So it will affect the natural dynamics of your system, but such isothermal conditions, right? So when you fix your temperature to be constant, such conditions may actually be relevant to modeling your system and to get experimentally relevant phenomena, right? So things such as diffusivity as a function of temperature, you need to fix your temperature, right? And fixing the temperature actually plays a role in determining the dynamics of your system. So even though this is a deviation away from what we would consider natural dynamics of a system, this may still be relevant to modeling the system accurately, or at least making the model experimentally relevant. There are several choices of thermostats that are available. So just like velocity integrators, right? There are several thermostats that are available, and these the choice of the thermostat basically indicates how the velocity is actually scaled. So what functional form they actually use, and do they introduce any additional constraints, right? So there are three famous or popular thermostats that are commonly used. One is the Berenson thermostat. So this introduces a thermal bath that is in equilibrium with your system with your system at hand, and the thermal bath is sort of coupled to the dynamic of your system. So there is a coupling term that is introduced that basically ensures that your system's temperature is always equilibrated with the temperature of this thermal bath. Nosey-Hoover thermostat basically extended this Berenson thermostat. So, but it considered the thermal bath to also be a part of the system. So, in Berenson, your system is separate, your thermal bath is separate. So, think of your system and your thermal bath as system and surroundings, right? So, thermal bath is still an external entity. But there are sort of computational reasons why that is not the most efficient way to scale velocities. So in Nosey-Hoover, you actually consider the thermal bath to also be part of your system. So your system now is your original box plus your thermal bath. And it also has this coupling term, right, being present, and doing this basically, so considering the thermal bath also as a part of a system changes the eventual energy that you are trying to sort of calculate or minimize. So it changes your eventual objective functions, which basically gives you a more accurate canonical distribution of velocities that you should actually be getting corresponding to the temperature that you want to control in your system. So given a temperature, you can get some kind of a distribution of velocities that is that represents a true system, and Nosey-Hoover is usually good at getting the true representation of velocities for a given temperature in a given system. So almost always Nosey-Hoover is a good place to start with when it comes to thermostats. So if you are new to molecular dynamics and if you are interested in doing constant temperature simulations, start with Nosey-Hoover. And the other sort of thermostat that is quite common is the Anderson thermostat. It uses a stochastic process. So, it is basically the velocities of individual particles are randomly reassigned and the way the reassigning happens is similar to the assumption that the particles actually undergo some kind of a collision. So, if the particle actually collides, then how will the velocity of that particle will be reassigned, right. So, it takes into account some kind of fictitious collisions and it chooses particles at random to reassign velocity. So, there is a lot of stochastic behavior being put into place in the Anderson thermostat, but in long term your Anderson thermostat can also give rise to this canonical distribution of velocities or the ideal distribution of velocities given a temperature. So, that is why this is often quite useful. But if you are new to molecular dynamics, almost always Nosy-Hoover is a good place to start if you are interested in constant temperature simulations. So, just like temperature, so we saw that we used equipartition theorem to define our temperature, right. So, just like temperature, other thermodynamic quantities can also be defined in our molecular dynamics, such as internal energy or potential energy, that is this term here, pressure being acted on by our system, what kind of chemical potentials do our system exhibit, how compressible our system is, so on, and compressibility is fairly important in the case of gases, right. So, just to give an analogy of how pressure is actually related or how pressure can be computed using molecular dynamics. So, pressure is basically your average force on the container, right, that is exerted by your system per unit area, right. So, you can sort of relate to, or you can write pressure as a variant of the ideal gas form. So, in an ideal gas, it is basically we are ignoring the R term here, right. So, if you choose the right dimensions, then you can set your R term to be 1. So, it is basically T by V, right, and N is the number of particles. So, pressure is related to this quantity here for an ideal gas, and then if you have a non-ideal system such as a non-ideal gas, a fluid or even a solid, then we will have this kind of a virial term, right, which represents how particles are interacting amongst one another, right. So, this is basically the position of relative positions of particles, and this is basically the force acting between the two particles, right. So, microscopically you can define pressure as so. For an individual particle, and then you can sort of generalize this expression in a macroscopic sense for your entire system. So, you can do an integral across all of your particles and you should be able to get your pressure term. So, just like temperature, you can define a pressure using your molecular dynamics, and you can actually estimate this in your calculations. You can estimate an average internal energy or potential energy of your system. You can estimate chemical potentials. You can also estimate compressibilities. Compressibility is alpha here, right. So, whatever thermodynamic quantities that you want to calculate, you can use these analogies to derive them or calculate them using your molecular dynamics. Now, you may be wondering, okay, what does it mean by calculating thermodynamic quantities in molecular dynamics, because in molecular dynamics I am trying to capture the kinetics of my system, or how my system is actually varying, right, with time. Basically, these thermodynamic quantities can be your constants. Right. So, for example, if you want to estimate pressure and let us say you want to control pressure, right, in your system, instead of controlling the volume of a system, you can actually control pressure, because pressure and volume are conjugate variables, right. So, instead of having an NVE simulation, you can have an NPE simulation. So, number of particles is the same, pressure is the same, and total energy is the same, right. So, we can sort of simulate the system under different boundary conditions, right. So, just like having a constant temperature is different from having a constant total energy. Same thing with respect to pressure and volume. So, your system will behave very differently when it is under constant volume or isochoric conditions compared to when it is under constant pressure or isobaric conditions. So, if you are interested in observing how the system is actually evolving under constant pressure, then defining this pressure quantity and controlling this. So, controlling the pressure to be a constant during your molecular dynamic simulation is very important, so that your system remains under constant pressure and the pressure is not varying to some asymptotic value, right, as you do your simulation. So for observing the behavior of your system under different boundary conditions, these kinds of thermodynamic quantities can be defined and they can be controlled or set in your molecular dynamics. So just like pressure, your chemical potential is typically used for simulating open systems. So let us say in most molecular dynamics we deal with the closed system where the number of particles is the same, but let us say you want to consider a system that is where you allow the system to exchange particles with some external reservoir, then you need to do an open system simulation where the chemical potential of the species that is being exchanged will be kept constant. So you need to find a way to calculate chemical potential within your system and then keep it constant with respect to your external reservoir. So that is why calculating chemical potentials can also be quite useful. The other sort of important quantity that can be quite useful in molecular dynamics, especially when it comes to tracking the evolution of your structure, is what is referred to as radial distribution function, right. So to understand radial distribution function, it is useful to understand what is referred to as a paired distribution function or rho of r. That is basically the probability of finding any two particles as a function of distance. So you have one particle at your origin at r equal to 0, and then as a function of distance, as you keep changing your r, you basically calculate what is the probability that you will find additional particle, some other particle, right, as a function of r. So this is basically referred to as paired distribution function. Radial distribution function denoted by g of r is basically a normalized version of this rho of r, right. So basically if your g of r is close to 1, then it indicates that there are no interparticle interactions, so your distribution of particles is very random, right, and any deviations from 1 basically indicates strong interparticle interactions, right. So usually in solids you will have large deviations from 1 because solids have periodic arrangements of atoms which indicate strong interparticle interactions, whereas in liquids and gases you will have more sort of or lower deviations away from 1. So I am just giving two examples of particle distribution functions for solid neon. So neon again is an ideal gas, so you can model this as a bunch of rigid spheres. So if you have solid neon, you see that your g of r has distinct peaks at different distances for a reference particle. This means that at 3 angstroms or so there are a lot of neon particles adjacent to a reference neon, right, and then the next set of neon particles is obtained at around 4.5 angstroms, and then the next set is obtained around 5.5 angstroms and so on, and in between you see that there is not many neon particles, right. So and this is representative of a solid. So in solid you have periodic distribution of atoms at very distinct sites, so you get peaks at very distinct distances. Whereas in a liquid, so this is the same particle distribution function in a liquid. So you see that the nearest neighbor or the coordination shell, the inner coordination shell is fairly well defined, but as you keep increasing distance the coordination is not very well defined, right. So the distribution becomes more and more random, so there is no real periodic arrangement of atoms, right, in a given liquid, right. So we see that paired distribution functions can be very different for an ordered disordered system or a solid liquid system, and these paired distribution functions are typically used along with molecular dynamics simulations to track a given structure, to see how the structure is actually evolving, right. And this is especially useful when you are tracking phase transitions in molecular dynamics. So let us say you start off with a solid and you want to actually melt it, you would typically be tracking the paired distribution function to see if your structure is actually molten. So this is a very useful quantity, and paired distribution or radial distribution functions can be readily calculated based on your structure, right. So these quantities can be readily estimated during the course of your molecular dynamics simulation. Just to give a couple of examples of how molecular dynamics are practically used. So these are both examples from our own research work here. So the first one we looked at an amorphous oxide material as a possible electrode in a magnesium battery. So these are beyond lithium ion battery systems, and once again here we were interested in the transport of magnesium within this amorphous structure. So you see here we are tracking basically mean square displacements. So think of these as delta r squares, right, as a function of time steps delta t. Basically the slopes here represent your diffusivities which are indicated here, right, and we see that diffusivities can actually vary as a function of temperature. So we have done simulations across different temperatures, taken the slopes to get diffusivities as a function of temperature. and this is the kind of trajectory evolution that you can expect to see in a molecular dynamics simulation. So you see that atoms are slowly moving across as a function of time, right. This is another example where we modeled lithium transport across an electrode electrolyte interface. This electrolyte is amorphous in nature, right. So we tracked how easily lithium can move within the bulk system, so bulk electrode systems and electrolyte systems and across the interface. So how easy it is for lithium to hop across this interface here. And these types of simulations, since we are dealing with amorphous systems here, both in this scenario and this scenario, these are very difficult to do with both density function theory calculations and also classical force fields. So we had to rely on machine learned interatomic potentials, machine learning based force fields here. And the nice thing to note here is that we are trying to model an amorphous system here. So this is basically the radial distribution function for this amorphous system, and we see that we see broad sort of plateaus here or shoulders appearing here, which is usually an indication of amorphization within the structure, because in a solid you will see very distinct peaks. We don't see such distinct peaks here. So these are the signatures that you are on the lookout for when you do dynamics. To see whether you have a truly amorphous structure, and then you track the displacements of individual atoms to determine their diffusivities here, and diffusivities here and here, right. So these are some kind of example studies that you can come across, especially on trying to understand diffusivities in different systems, right. Okay. So with that we will summarize and stop our discussions on molecular dynamics. So as mentioned before, molecular dynamics is a way to track trajectories for estimating kinetic properties. So we looked at diffusion as an example for a property that is very relevant to materials design. The choice of integrator and time step is very important in molecular dynamics. So we saw the importance of velocity Verlet and implicit schemes being used in molecular dynamics. Choice of force field, again there is a typo here, this would be force field. So choice of force field is also fairly important because it determines the accuracy cost trade off, right, and force field calculations are typically the most expensive calculations in molecular dynamics, so they determine the cost of your calculation. And the accuracy of the force field also depends on what kind of data you use to fit the force field to, right. The more accurate the data is, the more accurate your force field is typically. And temperature is a very important quantity in molecular dynamic simulations, and these are directly related to particle velocities using equipartition theorem. And if you want to control the temperature, you use a suitable thermostat, right, and you do velocity scaling. You scale your velocities using this thermostat so that your temperature is fixed during a simulation. And radial distribution functions are very useful. These can be readily calculated over the course of your molecular dynamics simulation, and these are useful for tracking structure, right, and examining structural evolutions in your system. So with that we come to an end on on our discussions on molecular dynamics. In our next lecture we will look at some principles of statistical mechanics and how they can be used for calculating some thermodynamic quantities. And they can also be extended for kinetic properties, but we will focus more on how statistical mechanics can be used for calculating very robust thermodynamic quantities. So with that I thank you all again for joining today's lecture. I will see you all in the next one.